Cool. All right, so today we're continuing on our ABCI discussion. Last week we did a pretty significant deep dive into the semantics of ABCI and the different ABCI connections and how they work and the relationship between consensus and the mempool. And today we'll focus a little bit more on the ABCI types and events and clearing up any outstanding questions. So before we pick up where we left off, does anyone have any outstanding questions from last time?
No.
Cool. So in that case, I will share my screen. And we'll get back to the ABCI. So last time we were going through the different messages here, and we sort of skimped through a few things. So we talked about the request begin block, which has some information about the last commit, which we looked at, and evidence, which I believe we also looked at. So again, the header here is basically the full header, the full Tendermint header with all the details. The last commit info is just some very rudimentary info over who signed the last block. So it doesn't give you signatures, it just tells you which validators in terms of their address and a Boolean and their voting power. And this allows the application to basically incentivize uptime. So validators can be rewarded and or punished for failing to sign some number of blocks. And then we have evidence, which is any evidence that's been included in this block. And again, it just lists the validator's address and voting power. So that was that. And then I think we were moving on to responses. And so there were a few key things we wanted to discuss. One is the event system, and the other is validator updates. So let's start with validator updates. So basically at the end of every block, when the app calls request end block, so after it's finished delivering when Tendermint calls request end block after it's finished delivering all transactions, it then gives the app a chance to return this guy, response end block, which can contain optional validator updates. And so basically in this list of validator updates, the app can return pub keys and voting powers that Tendermint should then update the validator set with. And so the rules here are basically that if it's a new pub key that Tendermint doesn't currently have in the validator set, then it'll add that validator. Otherwise, it will expect it to be an existing validator and it'll adjust the voting power to whatever voting power is given. And if the voting power given is 0, then it'll remove the validator from the set. And the expectation is that the application will only provide pub keys for validators that are in the set, that it won't, for instance, that it won't remove a validator that's not already in the set, so that you won't get a pub key that's not in the set with voting power 0. That's the validator. Yep.
The public key must it belong to some full node that is already somewhat in the system, or can it just be some arbitrary public?
Yeah, it can be arbitrary. So remember that there's no correlation between a full node and a validator. So they're not necessarily identified in any way. So the pub key is really some validator's public key. Presumably the app learned about it somehow through a transaction where someone, submitted a transaction that included this public key that said, hey, this public key wants to become a validator. And then it's up to whoever owns that public key to make sure they come online with some arbitrary full node and get connected to the rest of the network.
So from Tendermint point of view, the sort of the risk here is that this public key does not even belong to some full node. So actually we might not be even allowed to read it and send a message to it. So it's really like application responsibility to ensure this.
Yeah. I mean, it's not even a concept of sending a message to a particular validator's public key. Like Tendermint never assumes you can reach a particular validator, right? So it's really up to to the application and the user who initiated this change to make sure that a node comes online that has this validator key and therefore can start signing. And if they never come online, then assuming they're less than 1/3 of the voting power, it won't be a problem, they'll eventually get ignored. But maybe then, you know, they'll start showing up in the request begin block as validators who haven't signed, right? So right away they'll be in the validator set, and if they're not online, then they're not going to be signing, and then the app will get noticed, hey, this guy wanted to be a validator, but now he's not signing, and then eventually they might kick him out.
So is it important that you store public keys, not some kind of IDs? Do you use public keys at all?
Yeah, so Tendermint needs the public key in order to verify signatures. Because without the public key, it can't actually check the signature of the validator, so to verify votes and so on. But the application typically doesn't care about the public key because the application never really verifies signatures. The application almost exclusively handles addresses. That's why in the last commit info, everything is done. Everything is done using addresses. So this validator here, yeah. So you see these two different validator structs. One uses addresses. This is the main one that we use for information, but then this one is for the update. It contains the public key. And there's actually an ADR about this situation. So if you want to read more about it, I believe it's ADR 18 here, ABCI validators. It talks about you know, all this stuff about why it contains only an address or a public key, and so on. So we went back and forth on that quite a bit actually before we decided just to use until we arrived at the system we have now.
Okay, cool. Thanks.
Yeah. Okay.
And there's, so for the owner of the public key, there's no danger, right? If the application adds me as the validator, if I don't know about that and don't participate, I am not going to be slashed if I don't do anything, right?
Well, it depends on the application. So if you have, like in Cosmos, the only way to really become a validator is to start bonding, right? There's a create validator transaction that presumably is sent by the actual owner of that public key, but and they would bond some atoms in that transaction, and then other delegators would start chipping in atoms as well. And if they become active, then as soon as they're part of the validator set, then those atoms become slashable. And so if they're not signing, sure. But of course, anyone can try to register anyone else as a validator and start bonding. But if that validator doesn't come online, if that public key doesn't come online, then, you know, those atoms are liable to be slashed. So you can't really, it's not like there's coins directly associated with the validator's pub key, right? So you can't make someone else liable without their permission, basically, because you have to bond atoms, and the atoms that get bonded are independent of the public key. There's no association other than the fact that they were bonded to that key, right? So it's not like I could figure out, Joseph, what your pub key is, try to make you a validator, and then somehow get you slashed without you doing anything, because to become a validator, someone needs to be bonding atoms. And if you don't bond any atoms, then you have no atoms to be slashed. Whoever bonded the atoms would be in trouble, right? But there could be social engineering there. For instance, if you had your public key posted on a website and you said, I'm going to become a validator at some point, and someone else decided to take advantage of your good name and make you a validator sooner than later and start collecting validation or delegation, and you're not online yet with your key, then everyone who did that might get slashed. But presumably people would look, and before they delegate, they would see, you know, is this validator signing blocks or something, right? So, yeah. Does that make sense?
Yeah, thanks.
Cool. So that is the validator update. So that's basically that. And this can happen every block, right? That the app can return updates to the validator. There's also in the init chain, we also allow the app to initialize the validator set. And that way the initial validator set can be some function of application specific data. So the Genesis file has a bunch of app specific data, and then the app can decide from that what the initial validator set should be and return that to Tendermint, and then Tendermint will initialize. But that's optional because you can also just put the validators in the Genesis file directly if you want. That adds more flexibility. So that's basically it for validators. It's straightforward, kind of in the ABCI, but it has profound impact on these systems and what you can do with them. So the other thing we were going to talk about is the event system. So you probably noticed that a lot of the responses return events. So begin block, check TX, deliver TX, and end block. We'll just focus on deliver TX and what it means here. And really the idea here is that because Tendermint doesn't know anything about the contents of a transaction, the event system is a way for the application to provide some information essentially back to users of Tendermint so that transactions can be indexed according to some application specific notions, right? And so for instance, you might have a transaction that sends a balance from a sender account to a receiver account. And Tendermint itself doesn't know anything about the contents of this transaction. But from a user perspective, it would be very nice to be able to index the transactions according to, all transactions from a particular sender or all transactions to a particular receiver. And so the event system basically allows you to do that because the app can then return in the response deliver TX, it can return events that say this transaction had, this sender and this receiver and even this balance, and then Tendermint can index those things, even not knowing what any of it means, just using the strings it gets, and users can later query for transactions that satisfy some index, or they can subscribe to them over the WebSocket system exposed by Tendermint. So this is a very powerful mechanism for enabling all kinds of user client functionality. So if we look at what an event is, it's a quite simple system. It's basically every event. So if we look back, all these things return a list of events, and then an event itself has a type and a list of key value pairs. And the key value pairs are exactly what you would expect. It's in here, I think. It's exactly what you would expect. It's basically just a key and a value. They're arbitrary bytes. They are also generated by protobuf, but those that file is in the libs common. So we can look at it actually more directly. Libs common. So it's in here. There it is. So it's just key value pair. And then, we're using one protobuf file from another. And so the idea here is that every event, so a single transaction or a single end block can emit multiple events, and each event has a series of attributes. And the attributes are these key value pairs. And the key could be something like sender or receiver, like literally that string. And the value would be, the sender's address or the receiver's address. And then Tendermint has indexing options. So it can basically index everything that it gets back, or it can index specific things. You can configure that in the configuration file, and then users can query for those things or subscribe to them over the WebSocket. And so for instance, if you use Looney and, the Cosmos wallet, and you look at the transactions page, and it shows you a list of all the transactions for your account, whether you sent them or received them, that's using this mechanism, right? That's using the ability to query Tendermint for all transactions that have, the sender attribute of this address and the receiver attribute of the same address. Look for all transactions that emitted events like that, and then return them. And so that's how that works.
And it's essentially, Tendermint with respect to this functionality behaves like a database or data store of transactions.
Exactly. Yeah.
Or there is something else in addition to transactions, which you kind of are interested in querying.
You can do blocks too. Mm-hmm. So I'm not actually sure how fleshed out that functionality is, but the end block also returns events because you can run logic at the end of a block that's not really associated with a particular transaction. It's just associated with the block, say. But mostly the queries are for particular transactions, because that's really, that tends to be what the user cares most about. But for some of the staking and slashing stuff, it's more, it happens at the end of a block. And so then you'd want to know, which block did this happen in?
Okay. But if you would want to query application state, then I guess with a query, you have also possibility to get like sort of random information about the application itself.
Yeah.
Data are not stored by Tendermint. So
Exactly. So the event system is really just like transaction specific output. You can kind of think of it like responses in a way. Not really, but it's more like tags of what happened in the transaction. And then the application state can be queried directly using the query option. And it returns, a pretty hefty response with lots of stuff, including, exactly what you queried for, an optional proof, the height, the index in the tree. So the index is kind of redundant with the key. And so you can query for lots of different things.
Like what I don't understand here is like from the application developer point of view, it seems you need to know the application internals to be able to figure out what are the key values you should query for.
That's right. Yeah.
So there is no sort of way to standardize this at a kind of API level, or
it is application specific. We do have this data path system where we have some convention over what you're supposed to say here, but it's not very strong. And so it really is somewhat application specific how the queries work. Yeah. So I can show some examples there actually.
Have you discussed maybe about alternatives where this would be less application specific and when there would be a way to sort of maybe using more type systems try to
it's hard to use more type systems in protobuf. It's not sure what that would look like. This was kind of designed to be similar to HTTP, where you have the same issue, like the HTTP queries and API is always very application specific. Which sequence of things do you put after a slash and which arguments to get a particular thing, even if you have very similar websites, they might expose vastly different APIs. So I think from that perspective, developers are kind of used to this sort of thing. Certainly it'd be nice to have a little bit more standardization, but we're limited in how far we can really take that.
Okay. But at least having some kind of index or equivalent to the index HTTP page where you see the list of, or I don't know if it's index. HTTP,
yeah. We get like a list, a self-describing list, a self-describing API. That would actually be really nice. Yeah. Like we have with the Tendermint RPC actually.
Yeah, exactly. Yeah. Something like this. And then you don't need to read the source code to be able to code against the Tendermint application. Blockchain.
That would be really nice. Let's say query should expose some self-describing. Yeah, good idea. Cool. Any other questions? I think maybe the next thing that basically covers everything in this file. Okay, we can talk about the codes actually, because I didn't talk about those, and consensus params.
So what do you mean by non-deterministic? There are some fields that are marked as non-deterministic.
Great question. So the ABCI application is expected to be a deterministic state machine, right? Which is necessary for state machine replication. So everyone is expected to compute the same state and return the same results deterministically. But in some cases, in order to allow kind of more platform specific or user specific or whatever data to come through, some of the responses are allowed to be non-deterministic so that they can return kind of specific data about the specific query, right? So this might contain something like the time the query was made at, some log with like, local logger configuration and stuff like that, right? And so a lot of the responses have that, and they're really to facilitate kind of debugging and, specific responses that aren't necessarily the same on every machine, but are very specific to the request happening on this particular machine. So for instance, the fact that...
Yeah, it's not part of the state, right? It's just some volatile data that we kind of generate.
Exactly. Like for instance, a logger. You know, this could literally be the application's logger being returned back from Tendermint. I don't know if anyone actually uses it like that, but that was kind of the idea.
Okay.
So use of these two things isn't particularly well developed, but the thinking was that they might be useful for people to return additional information through that doesn't need to be deterministic.
Okay. So what is guess? Is it like application?
What's what?
There is this guess. There are these guess fields. Well, I didn't know you had guess actually.
Yeah. So so this is also so gas is basically here a generic way of thinking about resource usage. And I don't think, well, okay, it is used in Tendermint a little bit. And the idea is that you may want, so it is an application specific concept, like how much something costs. Sorry. And, but we do allow Tendermint to be configured to limit how much gas, whatever gas actually means, is used in a particular block. And so basically, when you send a transaction, you know, it's up to you to encode according to what your application semantics are, you know, how much gas is being requested or used, how much gas is being requested. And then there's this option here for the transaction to return, you know, some notion of how much gas was used. It's just like a single value, there's no unit. And then Tendermint can actually limit the size of a block, not based on bytes, but based on gas used, which is, you know, another way for the app in Tendermint to interact, to limit kind of what's happening on the Tendermint side, where basically the app can determine, you know, how much gas every transaction uses, and then Tendermint will only put so many transactions in a block according to how much gas they use. So it's just another way to think about resources in the system and communicate about them between the app and Tendermint beyond just, you know, bytes.
Okay.
And how do you calculate the gas, or is that up to the application to define that?
It's fully up to the application.
Okay.
Let's say if I run out of gas, what happens? I'm never committed, or what?
No. So like if what do you mean by run out of gas?
I don't know my gas value is 10 in the transaction, and Tendermint doesn't allow me to. Tendermint tells me there is not enough gas. What happens then?
So if the gas limit for a block is 5, and you have a transaction that uses 10, that transaction will never be included in a block. But if you have a block limit of 100, and a transaction uses 10, and there's already a bunch of transactions that are being put in this block, then your transaction will just have to wait until the next block.
Yeah, so I think here the important difference with maybe gas in Ethereum is that it's sort of not really the runtime concept. It's more like at a consensus level concept, or before block execution. So you use gas just to ensure that the size of block respects some application instructions, let's say like this, or requirements. But once we start executing transaction, we cannot just stop in a half of transaction because there is no more gas.
Right.
There is no such thing in Tendermint.
I see, but I can imagine that I can produce like 1 million of transactions with a very high gas value, and what happens? Does it block Tendermint forever, or what's going on there then?
Well, you can think of it the same as having really large transactions, like in terms of bytes, right? Because the block size is limited. So you can limit the block size you can limit it both by the number of bytes and by the amount of gas. So it's just another way of thinking about the size of a transaction, right? But the semantics around them are basically the same in terms of, you know, you'll propose a block up to a given size. So if you have more transactions and they're really big and they would cause you to exceed the size, then you have to wait till the next block. So same with gas.
Yes, but are they going to be collected in the mempool?
Yeah, they get collected in the mempool. Yeah.
So it's very easy to kind of produce a huge mempool just by setting the gas values.
But I guess here, as this is part of the check TX, if transaction has like very big gas, probably bigger than the block size, I guess it will not stay in the mempool. It will be dropped, if I'm not wrong.
Oh, okay.
I think that's right, actually. Yeah, if it's bigger than the block, it will probably be dropped. So we can look at all this, you know. Let's see.
Yeah, but like the interesting case is if you are just at a limit of the block size. But then this can be considered as a valid transaction. It's just then one block, one transaction.
Sure. Yeah.
Yeah. But if you're above, then it should just be dropped.
So there's this check here that basically checks based on the max gas. So if the gas wanted is greater than the max gas, then it's going to throw an error, and I think it will then get rejected by the mempool.
Cool. So it's not so easy to kill the system. That's good.
Yeah. Right. Okay. So, great. So there's these non-deterministic, talked about gas events. So the other thing is, so the data is basically the return value. So that's, you know, deterministic value that everything is supposed to return the same. And then the code. The code is sort of like a response code. Right now, the only thing that Tendermint enforces is that 0 means okay, and anything else means some kind of error. It doesn't have any notion of, you know, kinds of errors. And like we were talking about last time at the mempool, some kinds of errors really are fatal, like you couldn't even deserialize the transaction, and some kind of errors are like dependent on the state, and so they're, you know, they can't really be considered like malicious. They're just due to, you know, concurrency basically. But we don't really distinguish any of that at the Tendermint level. There are some open issues around potentially doing that, so that, for instance, we could punish peers for sending us mempool transactions that return certain codes but not others, right? So if a peer sends us, right now, if a peer sends us a transaction with that returns a non-zero exit code, we don't punish the peer, because we don't know if that non-zero code was due to something about our state. So like we received other transactions first that made this one invalid, or if it's due to this was actually a bad transaction that the peer shouldn't have forwarded, right? And so it might be nice to have some differentiation among the codes, so that specific codes actually refer to this is really bad, you know, the peer should be punished, versus, okay, this is just due to the current state. So that's the code. Now also at the application level, you may, just having a single integer to describe all possible outcomes, right, returns, isn't really sufficient, especially if you want to have a more modular application structure, right? So if you're building an application framework and people are writing different modules for that framework, and those modules are somehow supposed to compose together, and each module has its own set of errors and things that can go wrong, a single code isn't really gonna suffice to distinguish between errors from the different modules. And so that's why we added this code space string. And so the code space string is basically a way of namespacing the different codes, so that modules basically could freely indicate, you know, this was an error from my module, error 0 or error 1 or 2 or whatever, versus other modules could do the same. And so it's up to the modules to have a unique code space basically, but then otherwise they get the whole range of the code. And then having this code space now could potentially let us say, okay, we could reserve a code space for, you know, very explicit Tendermint errors, like, you know, the transaction didn't serialize or something else, or didn't deserialize or something else. And then we could use that to say, if an app returns something with this reserved code space, call it the Tendermint error code space, then peers would be punished for, or, you know, disconnected from, for sending us transactions that returned those kinds of errors. So it just adds a lot. It's just adding another dimension to the return values, so that we don't have conflicts in that, so we can be a lot more flexible. Does that make sense? Silence to me, yes. Cool. So that's basically everything in this file. So this should all really make sense now, I hope. And what we can do now is look at the docs and look through some of the code. So I will pull up the documentation.
I don't know if you if this wants to be covered, but last week you mentioned something about error handling and how it's a kind of a big rabbit hole within the ABCI.
Yeah. So that's in the docs, and I guess we'll get to it in the docs. So we'll just quickly go through, like, tour through the docs, and then we can talk about that as it comes up. Okay. So tendermint.com/docs, and then down the side here we have the ABCI stuff, and we have methods and types. So this is basically an explanation of the ABCI syntax, and some information about the different connections. So we could talk a bit about, so here the errors are right at the top. Very good. So I gotta get this. So some of the methods don't return any kind of error code, namely these ones. So if there is an error during that processing, it indicates some kind of critical failure, and there's really no way for Tendermint to recover from that. And so the expectation is that the app will really just panic. And then if the app stops, Tendermint will eventually stop, and then they just need to be restarted. And, it's up to the operator to come in and address it. Maybe there's disk corruption, or maybe there's a bug in the app or something like that. The other methods that can return some kind of user-based error return a code and a code space, as we just discussed. And so, Tendermint can do things based on those, but there isn't really a notion of like stronger error handling if something actually goes wrong in the app, because there's nothing really Tendermint can do. I mean, Tendermint's expecting that, these things are roughly a single unit, the app and Tendermint. And so if something goes wrong at the app level, Tendermint has no choice really but to halt. And so we don't really make any accommodations for more robust or more sophisticated error handling, because it's not clear what we would do with that other than shut down a little bit more gracefully. So, yeah, I don't know that there's much more to say about that.
So if the app is in some infinite loop and doesn't come back, what's happening then?
Tendermint will be stuck. Yeah. If the app is in an infinite loop and doesn't come back, Tendermint will just be waiting. It doesn't have any timeouts as far as I know.
Okay.
So that would be bad. But that's the app developer's responsibility.
And so when you say that the app will panic, like it sort of makes sense if it's the same process, but if we have different processes, then how you would detect that that there is something wrong?
The app will panic, which will kill the connection between them. And then the next time Tendermint tries to talk to the app, it'll find that it's not able to send messages over the connection. And then it will exit. And it'll print some error that's like, hey, the app seems to be disconnected. Please restart both Tendermint and the app.
Okay.
Yeah. Okay, so the event system, we talked about the event system. Here's some, examples of exactly the kind of thing we were saying. You could have different, you label the types. So here here's an example of validator provisions. So these are like rewards being paid out. And, here's the address, the amount, and the new balance, basically. And here's saying, oh, this validator got slashed. So that's an event. And here's the address, the amount, and the reason, right? A note on determinism, everything needs to be deterministic. Sources of non-determinism. So all this would be bad and can destroy consensus. This one especially, because that's more application. This stuff is more really up to the application. Of course, some of this you can't really control. Yeah. And then block execution, we discussed, basically looks like this. Begin block, multiple deliver TXs, end block, and commit. And then this basically goes through all of the messages and describes all the arguments and all the response values and how the message is used, just at a kind of cursory level. So we don't have to go through this in detail because we've really talked about it all. But if you're interested in reading through this and seeing if it makes sense. At this point, it should definitely make sense. If something doesn't make sense, open an issue. And then at the bottom, after all the message types, then we have the actual data types used. So, the header is the Tendermint header, version, validator update, and validator, and so on. One thing I guess that's worth noting is the pub key. So pub keys in Tendermint use Amino, which is our protobuf 4, also a variant of protobuf 3 basically, and they are encoded as bytes with some kind of prefix, and the prefix is this like amino specific thing that distinguishes different types from each other. But because we wanted the protobuf to be independent of amino, and this actually took some time to get here, and I think there's ADRs about this as well, we have a different kind of structure for how we send pub keys over amino, and it's basically a type string and some data bytes. And so, over protobuf, over ABCI. So the type string is basically just a very simple string like this, ed2519, and the data is basically the raw bytes. And so, this is relatively extensible, but right now it's used very simply, but it does mean we have multiple ways to encode a public key, one through protobuf over ABCI and one using amino over the wire, like when we send a pub key to peers, for instance. And hopefully down the road, these will converge. We have plans to move Tendermint to basically update amino to be fully Proto 3 compatible and to consolidate this difference using protobuf's well-known type any. So protobuf basically has a structure that basically does this already, and it has a name. So we'll move to using that, and that way the pub keys in Tendermint and the pub keys in ABCI will become the same. But in the meantime, they are encoded slightly differently. So that's just a gotcha that's worth mentioning. So that's all the types. We didn't really talk about proofs. They're not that well developed, and they're not used yet in Tendermint. They're more for users. So this is basically when you make a query, the app can return a proof of the query, which is basically a proof that the result is in the Merkle tree, right? So it's like a membership proof. I think it can also return non-membership proofs, so like that something is not in the state. And we've tried to provide a little bit of structure around the proof system, but going into that in detail is probably a topic for another dev session. But for instance, this is important for IBC, where we're trying to standardize the formatting of proofs, of Merkle proofs, basically. So then in this applications page, we talk in a lot more detail about how the ABCI is actually used, and as a developer, as an app developer, what you need to be aware of. So for instance, that you're expected to maintain 3 distinct states, one for the queries, one for the consensus, and one for the mempool. And it talks a little bit about the relationship between all those here. So we talked about that kind of at length last time. Transaction results. So here's a bunch of detail about how the gas works, and it's all because of the max gas that you can configure as a user. But this is a consensus value, so this needs to be configured at the beginning and fixed. One thing we actually didn't talk about is these consensus params. So why don't I actually briefly pull those up? So
can I just ask a question about the consensus
Sure.
proofs before?
Yeah.
Not consensus proof, about proofs. So the proof essentially is just some information about the application state.
Mm-hmm.
And so if I'm kind of thinking about this fork detection case, that we might actually reuse this mechanism to sort of publish the vote set in case you're suspected, and then we have a kind of proof of both existence or non-existence.
So the proof system there is specifically about Merkle trees. So it's specifically about providing paths in a Merkle tree to prove that some leaf is in the tree. And so if we don't have, if we're talking about a different kind of proof, like for the fork detection stuff, that there's just some set of votes, they're not necessarily in a Merkle tree that's been committed in the consensus, then I'm not sure that would apply.
No, I was thinking just that, like, if I could write a vote set to the Merkle tree, then I can use proof mechanism to prove that, sure, like, it's sort of published.
Yeah, for sure.
And then people can hear it. And it's even more important if it's not published. Like, so if, for example, we say you have 1 day to publish your vote sets and prove that you indeed publish them, this might be a way to do it. And the other way around, if you haven't published it, we kind of have a timestamp that after this thing, there was nothing written in your Merkle tree. And so, although the tricky, or what is kind of tricky, is that every validator will sort of write different data to its Merkle tree. And I guess this part is problem, because here the data store is supposed to be the same at all validators.
Yeah.
So, but it's kind of, sorry for digression. It's,
so we do want that proof system to be like generic and so usable anytime someone has a Merkle tree for writing proofs to it. So if there's a Merkle tree, you should be able to use it. There are some limitations there that are being explored in the IBC design. If you're interested in that, you can check out ICS 23, but that's a side topic.
Cool, thanks.
So the consensus params, so these are configured in Genesis, and they determine a bunch of details about the consensus that are must be agreed on by everyone. So these are, consensus parameters, and we split them in 3: block params, evidence params, validator params. So the block params are basically determine the size of a block, and they can be determined both in terms of bytes and in terms of gas. And if both of them are set, both must be satisfied. The evidence params basically determine the maximum age of evidence. Currently, this is in heights, and the reason to do this is to is really for spam prevention. So to prevent really old evidence that we're not going to be able to do anything about from being from continuing to be broadcast. So this roughly should map to the unbonding period. The fact that this is in heights and not time is kind of an open issue, and we need to do something about that. And then validator param is basically just a list of allowed pub key types. So in Tendermint, a pub key is an interface, and there are at least 3 implementations right now. There's the ed2519 key, the SecP256K1 key, and then a multi-sig key. And so we basically restrict what kinds of keys can be used by validators with this consensus param. And so here you just provide a list of strings to indicate that. Now, these consensus params can be updated with every block in the same way validator sets can be updated. So the app can just return a new set of consensus params that will then take effect for the next block. So if the app needs to, increase the block size or allow new public keys or something like that, it can do so. So that's basically that. So going back to the documentation. So yeah, we were talking about gas. So we talked about all that. So this is all the details of how gas works. If you want to read through it, check TX and deliver TX details. Really it's all about the only kind of error we check is whether or not the code is 0. And so right now in the mempool, if the code is not equal 0, it gets rejected from the mempool. On deliver TX, because it's already in the block, if the code is not equal to 0, the transaction is considered invalid, but it's still included. There's nothing really we can do about it. Validator set updates, again, we talked about there. There is a max total voting power that's specified to minimize overflow issues. And so apps are responsible for making sure their voting power is within that limit. And then the validator set updates happen during init chain and during end block. Here's, this should be very familiar now. Again, talking about the pub key type, what that should actually look like, and the rules around the voting power. Then there's the consensus params.
Are we currently to deny a transaction from entering the block since it's invalid, or is that like
So if it's invalid in the mempool, then it won't be included in a block by a correct proposer. But it's possible for a malicious proposer to include bad transactions in a block, and it's also possible for a transaction to be semantically valid, like I guess syntactically valid but semantically invalid based on the state. So it might have been, if like you have an out of gas execution in the EVM, for instance. So that's a valid transaction. It pays fees. It has a valid signature. But then what the user expected to happen didn't happen, right? And so we return a non-zero code. So this goes back to what I was saying before about different kinds of errors and how we really ought to distinguish better between them. Errors that are really like, due to something invalid, and errors that are just, due to concurrency and statefulness. Yeah.
So I guess I missed about this max total voting power. Is it is the parameter that you set once for the application, or can it also change?
This is hard-coded.
Hard-coded, okay.
It's basically to deal with overflow.
Okay.
Because it's an int64.
Okay, but that's a lot, right? So you can...
It's a lot.
Yeah.
But you'd be surprised how quickly you can reach that. Well, maybe you wouldn't be surprised, but it's not out of reach. Let's put it like this. Yeah.
Okay.
Yeah. So voting power, consensus params, again, details on all the different parameters. This one actually got removed, so we can remove that. And updating the consensus params, and then notes on the query and the query proofs. So there's a lot of detail in here on how the proofs work, but I don't know how well used this system is yet. So it's probably going to still undergo some changes. And then one thing I didn't actually, here there is some details about the paths and some standardization around paths. So, the expectation is that the query paths will have high level differentiation like /P2P, /store, /app. It's not really enforced too significantly, but there is one place where Tendermint actually uses the query system, which is for filtering peers. So basically what this allows you to do is it allows Tendermint's peer connectivity to be influenced by the application. So if configured on startup, when Tendermint connects to a peer for the first time, it will make a ABCI query with the information about the peer and give the application the opportunity to accept or reject that peer. And so the query basically looks like this. And there are two kinds of queries, one where we query according to the address, so the IP and port, and one where we query according to the peer ID. And you can configure both or either. And then the app can return a non-zero ABCI code, and then Tendermint will refuse to connect to the peer. So this is one example where the query system allows Tendermint's behavior to be influenced in an application-specific way, but through a non-consensus-based mechanism, right? Because this doesn't involve consensus. This can be a fully local subjective setting. It doesn't have to be consistent across the different nodes, but it allows the application to influence Tendermint's peer behavior. Looks like I'm missing a slash here. I'm gonna note that to myself.
So if I'm a faulty client, I guess I can kind of influence my neighborhood and make, kind of invite only my friends there, right? My faulty friends.
Yes, you could, yeah. I mean, you can restrict how you want to connect. That's up to you. This just allows you to do it through the application. So you could implement some logic around whether you want to, whitelist, blacklist, etc.
But you cannot affect the others peer list with this mechanism.
Right.
It's just you can locally decide to whom you want to connect, but you cannot force someone else to connect with this mechanism to subset of peers.
Right. This is just local modification of a bit of node behavior. Cool. So the last thing in here is the crash recovery system. And so This is in order to make sure that, you know, if the application fails or Tendermint fails, that when we restart them, that they sync up and they're in a consistent state, because they could have been, you know, in different processes and they could have crashed at different times. And so this basically explains in detail how that works. And it's all based on the info method, which is called at startup. So when the processes first start, Tendermint will call request info, and it'll get a response info with information from the app about basically the latest state it has committed. And Tendermint will use that to figure out what information needs to be replayed against the application so that they are synced up again. And so there are many different situations where we could have failed, depending on what Tendermint has persisted to disk versus what the application has persisted to disk. And so this crash recovery claims to deal with all those scenarios. As far as we know, it does. But this is critical to actually making this a real system. Otherwise, you can end up restarting and those two being in different states and not being able to sync them up. So this took a while to get right, but it seems to work. But it would be good to capture it more formally, for sure. And that's basically it. So, you know, we might do another dev session on this specifically and go through the code and talk about the different cases where this happens, and it'll expose us to a lot more of Tendermint's internals. The only other thing in the docs here is the details on the client server. So this is, you know, if you're implementing your own ABCI server in a new programming language, or you want to implement your own client, you would look at this. But if you're just an application developer and you're just trying to understand the ABCI, this is all very low level. This is really like, you know, how the things communicate over a socket. Yeah. And that's that. Any questions?
I just want to say that it would be interesting to look at the crash recovery at some point in more detail.
Yeah, for sure, for sure. That one I might actually have to prepare for. At least review in advance, I would say. Yeah. Cool. Any other questions? We could, I could briefly show some code. We do need to wrap up, but just to give an idea of where certain things happen and how, which might be useful. So, so first of all, if we're talking about the consensus, well, first of all, oops, in the node, I think there's a system. Yeah, so the filter peer system that we were just talking about for queries is set up here. So, you know, if this filter peers option is set in the config, then it will call, then it will set up basically this closure to call the query system on the app with this path, like we saw, with the information from the peer. And then, you know, based on the result, we'll determine whether or not we connect to the peer. So these filters are then passed into the peer layer and used to filter peers. So that's one. As for the consensus, so all of the ABCI stuff is actually encapsulated in this apply block method. So from the consensus package, you don't really see any ABCI other than this apply block method, which if we then go in there has all the gory details about what it takes to apply a block to the Tendermint state. And really then if we dive in a bit further, it's all in here. So we first call begin block. We call that synchronously. And then asynchronously, we call deliver TX, which means the deliver TXs are fired one after another to the app. And the next one is sent even before we receive the response from the previous one. And so those responses are kind of coming back asynchronously using this callback function, which is basically just tracking, you know, whether or not they're valid and adding the results into a map. And so nothing particularly interesting there, but just to point out that that's what's happening, that the begin block happens synchronously, the deliver TXs happen asynchronously. The idea there being that we don't want to wait to send more transactions before other ones return. So this allows us to kind of quickly forward all the transactions over the wire. And then finally, we call end block synchronously, and then eventually we call commit out of that. So we save all the ABCI responses, we update the validator set based on the end block results, and then eventually we will call commit. Yeah. So that's the consensus stuff. The other thing maybe worth looking at is the mempool piece, where basically we have this mempool checktx function, which does a lot of work because it has a cache and other, does a bunch of checks. At the end of the day, really it's just calling this checktx async. So again, it's an asynchronous ABCI call, so it just forwards the thing over the wire, and then asynchronously somewhere else or concurrently somewhere else is waiting for the responses. And those responses are in these CB functions. It's actually quite complex in the current mempool implementation, but for instance, we can see in one of these that, I think in this guy, oops. Yeah, here we basically receive everything back. We expect it to be a response checktx, and we do some post checks. So this is like checking after the fact for if the gas is too much, and then we store everything in the mempool, and then it's eligible to be sent to other peers. Otherwise, if it if the checktx code was not okay or there's an error, then we reject it as a bad transaction and we remove it from the mempool. So this mempool implementation is actually quite complex, and it's difficult to reason about because there's a lot of concurrency, but that's something to deal with another time. I guess that's that. Was there anything else anyone wanted to see in particular, or should we wrap it up?
I think due to time constraints, we should wrap it, and then if we can have a follow-up one as well, if more people ask.
Cool. Any final burning questions? All right. This concludes the ABCI dev session. Thank you very much for watching.
Thank you.
Thank you.